Our next two speakers are really two of the leading scientists inside the space community, and we're really quite honored to have them here today. They'll present two presentations today, and I think the main issue is that both of these individuals have an incredibly high command of what is going on, what is going to be happening, and what we can learn and do over the next coming years in space exploration. So I'd like to introduce the first of our two speakers for the next session. And that is Dr. Laurie Leshin, the Director of Sciences and Exploration at the NASA Goddard Space Flight Center. Before assuming the position of director in August 2005, Dr. Leshin was the Dean John Whiteman Dean's Distinguished Professor of Geological Sciences and the Director of the Center for Meteorite Studies at Arizona State University. She recently completed service on President Bush's Commission on Implementation of the United States Space Exploration Policy, a 9-member commission charged with advising the President on the execution of his new vision for American space exploration. Leshin received the NASA Distinguished Public Service Medal in 2004. In 1996, she was the inaugural recipient of the Meteoritical Society's NEAR Prize, awarded for outstanding research in meteoritics or planetary science by a scientist under the age of 35. The International Astronomical Union recognized her contributions to planetary science with the naming of the asteroid 4922 Leshin. She received her BS in chemistry from Arizona State University and her PhD in geochemistry from the California Institute of Technology. Please join me in welcoming Dr. Laurie Leshin.
Ooh, you read the whole thing. That's always scary. I should just do the asteroid part. That's the only thing. That's the cool part. All right, good morning, everybody. It's really thrilling to be here with all of you to get to talk a bit more about the science part of what we're planning for the moon. Myself and Paul Spudis have both been involved in this. Paul's going to get up and give you some thoughts on where we stand with the vision after I'm done. I'm going to stick a little bit more to the science planning. How many of you watched President Bush's speech back in 2004 when he came to NASA headquarters and announced the VSE? I was a professor at Arizona State, as George just told you. I was a professor at the time. I was sitting in a room with about 40 colleagues, all just curious about what this speech was going to entail. And I remember getting really excited at that moment, feeling like, wow, this is going to open up just a ton of opportunities for science. And how am I going to figure out how to get involved in this and how to help figure out the best science to do? And I'm a little professor at Arizona State. Well, 2 weeks later the phone rings and they say, yes, this is the White House, and will you please come and serve on this presidential commission? And it was just such a thrill and an honor to get to do that with 8 other colleagues and present some recommendations to NASA about how they can most effectively move forward with the vision, including a science agenda that was pretty broad and encompassing. But that wasn't really enough for me to be able to just sort of write some recommendations and then go away. So I joined the agency about 18 months ago, coming to NASA Goddard, which is has the largest science organization within NASA, and that's been such a thrill to get to be involved inside the agency now. And as part of my role there, I've been serving on the lunar architecture team as the co-lead of the science capability focus element, which is basically a longhand way of saying I've been leading up some of the science planning activities within the lunar architecture. And so I thought I would tell you a bit more today about what we're doing in that forum and engage you all in some discussion about what science we want to accomplish on the moon. So you're now all officially part of the science community. If you didn't know it, you are now. And we want to get your input on what we're up to. So let me say that I'm probably going to take up a good part of most of the half hour here, but we actually have an hour set aside at 2 o'clock this afternoon in the lunar track that I'm mostly going to leave pretty open to discussion. So if people have follow-up to Neil Woodward's presentation this morning or my discussion right now, and more questions there, more discussion that y'all want to have, come at 2 o'clock and we can make that very give and take and very interactive, okay? And I've also got an update on the Lunar Reconnaissance Orbiter, that LRO mission that's going to launch next year. If people want to hear that as well, we can do that this afternoon. Okay, so next slide, please. Okay, so the main message I want to get across to you today is two things. One, the moon presents a lot of very compelling opportunities for scientific discovery, and it's going to be extremely exciting having the capabilities that we're developing in the vision, both on the moon, but also beyond that. As someone mentioned earlier, the launch vehicles we're developing and things are going to really enable a bunch of incredible new science. We also, of course, need scientific knowledge to be able to help us design those systems most effectively and efficiently. But we're going to focus a bit more today on the cool science we can do once we get to the moon. And so here's just a few examples of the kinds of things that we can learn. The moon is really quite an amazing place because it is a recorder of the emergence of our Earth-Moon system. Just at the time that life was emerging on our own planet in the first, say, 500 million years of Earth history, we have a great record of that time on the moon that has been erased from the Earth by erosion and plate tectonics, and basically the Earth is really good at covering its tracks. But there on the moon is preserved the evidence of what the Earth-Moon system was like as the solar system was being born, essentially, and as life was emerging on our planet. So there is a record there to be read. It's as if the history of our planet is a book, and the first few chapters have been ripped out if you're trying to study the Earth. By going to the moon, we can actually read those first few chapters. So that's going to be a key part of the exploration that we want to perform from a science perspective. Understanding the surface and interior of the moon. The moon is a terrestrial-like planetary object. We don't understand very much at all about the interior of the moon, so we need to explore that as well. Permanently shadowed polar regions, which you've already heard a lot about and we're probably going to end up living next to on the surface of the moon, contain a treasure trove of potentially fabulous science, of which we know very, very little about. They potentially contain volatiles. We don't understand yet how those volatiles got there. We don't understand what volatiles are there, how they're stored, how they survive over time. There's a ton of great science to be done there. The lunar regolith, that dirt and dust that's going to cause us potential problems, is also a great scientific treasure trove in that it is a tape recorder of the history of our sun, because the moon is exposed out in space. It's getting bombarded by the solar wind all the time. And so if we can find great exposures of regolith, the right exposures of regolith, we can drill down and really read the history of our star and use that to help understand not just the history of our planet Earth, but also understand how stars work and the history of stars in general. And then, of course, that's sort of science of the moon. And then we can do science from the moon, using the moon as a great platform for observations of the Earth, of space, and of the sun. And so we'll talk a little bit more about those areas as well. And finally, because there's no life on the moon yet until we start living there, it's a great way to go and test protocols for when we'll go to Mars and to understand how clean or dirty we are when we're exploring a planetary surface, to understand what it takes to protect and preserve both the planet that we're exploring as well as people back here on Earth when we return things. So it'll be a great test bed for our planetary protection protocols. Next chart, please. Thanks. So I want to tell you a little bit about what we've been doing in sort of the science part of the architecture team. I'm going to step back and talk about how we start having these conversations about science on the moon. And it basically came, and Neil mentioned some of this earlier today, from this list of lunar objectives that were generated, and he talked a bit about the RFI and all that stuff. Well, and I was involved in a workshop last April, and several people in this room I know were there as well. Some of them were even on my team in that workshop, where we generated lots of possible objectives for lunar exploration. I'm going to show you a bunch of examples of what these objectives are in the science area coming up here. But basically, we spent months and months sort of pulling in ideas for these objectives and sort of lumping and splitting them, eliminating duplicates and such. We got them not just through this workshop last April, but through the RFI, through lots of international contributions, and other groups provided ideas there. And so we refined those and got down to a list of about just over 180 objectives in lots of different areas, not just science. The science objectives, sort of the pure science area objectives like I'm going to talk about today, it's about 50 of those are science objectives. And so we sort of went through this culling process, got down to these 180 objectives, and then from that we took the science objectives for our part of the lunar architecture team. Come next slide, please. And as you already heard, I just want to point out again that we had these sort of 6 themes that also emerged from this discussion of objectives. And you can see that scientific knowledge is one of those, and it emerged very strongly last April. I will tell you that, it's been said that we're not going back to the moon first for science. That's not the reason the vision came into being. It was not primarily a scientific outcome that said, okay, this is what we're going to do. We're going to send people back to the moon in order just for science. But it's very true that when you get people together, it's completely clear that everybody from all parts of NASA on down wants to accomplish great science on the moon. And the moon is there for us to expand human knowledge with, so we're definitely going to take advantage of that. And a lot of the science that we do on the moon will help also contribute to other objectives like human civilization, learning to live and work on the moon. In order to learn, live, and work on the moon, you need a lot of scientific information about the materials that you're dealing with. In order to do ISRU, you need to understand those materials. In order to live safely on the moon in the radiation environment, you need scientific knowledge of what that radiation environment is. You need to develop predictive capability there. So there's a great synergy between the scientific exploration we'll do and many of the other areas that we're going to work in on the moon. Next slide, thanks. So I love this slide, and Neil went past it kind of fast, but this is one of the most fun things that we've done in the lunar architecture team, is to kind of lay out a notional outpost location. He mentioned Shackleton this morning. Shackleton's a crater near the south pole of the moon. Shackleton has not been selected as the site, I will say. We were using it as a reference location. We have decided through the lunar architecture team, as he mentioned, to try and do polar exploration for many of the advantages that presents. And so we use Shackleton as a reference crater, but really we need the data from the Lunar Reconnaissance Orbiter in order to really map out the poles and figure out the most optimum location. So we're working on sort of how are we going to select that final landing site. We're working on developing those criteria. But this is good sort of notional outpost location. So what you're looking at there, the sort of dashed line along the top is the edge of the crater, and the grayed out areas are the areas of near perpetual sunlight, at least as far as we know them at this point. And what you can see in the top image there in color is the illumination map for Shackleton crater. And there's that little picture right inside there with the red arrows. Can you guys see that? That's the National Mall in Washington, D.C. for scale. So at one end is the Capitol, at the other end is the Lincoln Memorial. So that gives you a sense of the size of the area that we're talking about here. It's a pretty sizable place to go hang out for a few years or decades. And then we've sort of laid out places where we land a bunch of the landers, where we might live, the habitation zone you can see. And in the middle of that, if you're looking at the habitation zone there, in the middle of that little tiny dashed circle is a model of the ISS to scale. So that little fuzzy thing that you can't even see is the ISS. So that, to give you a sense of the scale again of this outpost location. And then over on the left, or is it right for you guys? I don't know. Part of the slide, the observation zone, the part that says to Earth. Well, I kind of call that the science farm. You can imagine setting up observation locations either to look at the moon to look at back at Earth, or setting up your geophysical research station and things out there a bit away from where the people are shuffling around all the time and kicking up dust and such. So this gives you a sense of the kinds of things that we're thinking and talking about. And when we think about performing science activities on the moon, we're thinking about it in the context of this outpost. Next slide, please. So here's what we've done on the science capability focus element. We've taken all those 180 objectives that were generated through that huge process that are not all science objectives. We've taken all the science objectives from that. In certain cases, non-science areas, we looked at what NASA was most interested in doing and sort of culled those objectives down to a smaller list. In the case of science, we actually have been carrying all of the science objectives because typically the scientific community tends to want to tell you what its priorities are. It doesn't want NASA to prioritize for it, and I certainly don't want to do that for the science community. So we've actually been we've made an assessment of all of the science objectives that have been proposed. And again, remember, those objectives came in from 14 different space agencies and countries, from all sorts of different communities. So it really is a very exhaustive list of cool science we can do on the moon. What we did was we took all those science objectives and we deconstructed them. We asked the question, and again, I'm going to show you some examples of these in a minute. what kind of capabilities are going to be required to execute this objective, and then we compared those capabilities. Is it an orbiter? Does it need to be a lander? Does it need to go to lots of different places? Is it a giant instrument? Is it a little instrument? That kind of thing. And then we compared those with the architecture that's emerging to allow us to say, how much science are we really going to get out of this architecture that NASA is proposing? So that's kind of what I want to show you is what kind of science are we hoping to do, and how well is that fitting in with the architecture that's emerging from NASA? So we developed a way of measuring sort of the goodness of fit of these different science objectives with NASA's architecture that's coming out. Okay, so let's go on to the next. So what we've done when we created these ratings is this is sort of the architecture sort of at a high level. So again, it's a polar outpost-based architecture. All missions in our assumptions right now are going to or near the outpost. Now, Neil mentioned this morning we are still looking at sortie options, and the systems that we're constructing have the capability to go other places. But just in terms of the core architecture, we're focused on that polar outpost location. In addition, there'll probably be some orbital capability as well, so things that need to be done from orbit can fit into this. Initially, we're looking at 4 crew for sort of 7 to 14 day missions, followed by longer missions. They actually get up to 180-day stays pretty quick in the architectures that we're looking at. So that's very exciting. We'll have people there for long periods of time. We did assume that there's some capability to fly robotic missions, especially before the humans arrive, and I know there's been discussion here about the current state of the lunar robotic program, and it's not as large as we'd hoped after LRO LCROSS, but I'm with Pete. I'm optimistic that we're going to figure out ways to either fly our own missions, either through ESMD or SMD, or to really work closely with international partners who are very interested in flying robotic missions to accomplish some of our science and exploration needs, and even to piggyback onto those missions. I'm very optimistic about that. Okay, mobility of the crew from the outpost site for the early phases of this, and we were really looking up through maybe say through 2025 or so, what kinds of things we might be able to accomplish. We're assuming that we're going to have relatively limited mobility, sort of Apollo scale mobility, 10 to 20 kilometers away from the outpost. In fact, I'll tell you right now on the architecture team, we're looking at much more significant mobility possibilities, and there's some really interesting ideas emerging that's not officially in there yet, but they definitely are. And especially from the science perspective, we're really pushing. We say, no, we want 1,000 kilometers. Why can't we have 1,000 kilometers? So, but for this assessment, we really looked at things that stay relatively close to that outpost. We're looking at about 500 kilograms of down mass for science on each of the crewed missions. That's something that the architecture team has really bought into and is holding on to and preserving. This is great news for science. And about 100 kilograms of sample return capability. Now, again, that's about similar to what we did on Apollo. Some of us are pushing really hard to get that number upped, and we're starting to get some good traction in the program to try and increase the amount of material we'll bring back. I will tell you, I will confess, I study rocks for a living. I want the rocks. I want them back here in labs on Earth. So, next. So here, this might be terrible, but I'm gonna show you some histograms. So here's the color scheme, and we'll talk about what all these mean. So what we did was we took each one of these objectives and we compared it against the architecture, and we said which ones look like they're really good, we can really accomplish those, and which kinds of things look like we're not really gonna be able to accomplish them, and so we can actually make an assessment of how the architecture is doing relative to science. So if something got rated green, it means yes, you can do it. So there's kind of 3 of these that are important. The green is important. So green means good. Yellow means, well, you could probably accomplish part of this with your outpost-focused architecture, but really to sort of say that you're largely completing that objective, you're going to need to do other things too that aren't in the architecture. Pink means, you know what, you're really going to have to do something different. But you could do that with just robotic missions. You don't necessarily have to send people other places, but you need to send robotic missions other places on the moon in order to accomplish the science objective. And finally, if something's red, it means, well, really, you've got to add something else like human sorties or some other kind of capability to the architecture. So green is good, red is not so good, and yellow and pink are kind of in between. Okay, next. So here's actually, if we go and look at overall, so there were, again, about 50 sort of what I would call pure science objectives, and then we also included about a dozen that were in the area of sort of environmental monitoring and operational monitoring. I'll talk a little bit about those. And if you go through and do this assessment overall, and we did this as a team, Paul was a part of this, the next speaker up here, and as well as about a dozen scientists around the agency, we came together, we each rated things, we got together, we fought it out, and we came up with a set of consensus ratings. Here's what you see. So 37 out of the 62 objectives are rated green. Now it's almost 60%. So the bottom line here, and this is great news, is that we provide a lot of different opportunities for science through this current architecture that's emerging from NASA. And now we need to really consider priorities, because first of all, there's probably not enough money to do everything that's green, and secondly, there's probably some stuff that's yellow or pink there that is things that are really, really important science objectives. And so we really need to figure out how to get those incorporated into the lunar program as we move forward. Next chart, please. Okay, so what I want to do is just very quickly, and again, we can do this perhaps more slowly this afternoon in the longer session, is give you a flavor of what some of these objectives are, just so you can kind of see what I'm talking about here, and then show you in each sort of sub-discipline area what we're talking about. So probably the biggest one, and the one that most people think of, is sort of the planetary science or geology type objectives. Things like understand the internal structure of the moon, or understand the composition and evolution of the lunar crust and mantle, so that we can understand the origin of the moon. Look at the distribution of lunar volatiles, again, understand those polar shaded regions. And things like characterize the impact process. The moon is a great natural laboratory for understanding basic planetary processes like volcanism and impact, especially impact, where we don't have too many great examples here on the Earth. Next. Thanks. So, okay, for that subset of objectives, here's the ratings. Again, you see a lot of green there, and there's a lot of things that require field work that's sort of non-site specific, things like regolith studies and these understanding impact crater studies that we can very well do at an outpost site, or things that are polar focused on volatiles will work really well at a polar outpost. Yellow objectives here and pink ones are pretty important in that they are things where you can learn something, the yellow objectives, you can learn something from doing sampling at the outpost site, but really we want to visit multiple sites on the moon to understand its diversity, to understand the history of impact on the moon, and so we really are going to have to figure out how to visit some other sites. The pink objectives here are things in the geophysics area where, for example, you want a distributed net of seismometers. You could probably deploy that robotically, so you don't necessarily need people to go to these other sites on the moon. But having one seismometer at the outpost site, it's okay, but it's really not going to advance our knowledge of the deep internal structure of the moon. So there's a few things there that we really do need to work on to get those incorporated into our program as we move out. Next. Astronomy and astrophysics. The moon has a great potential to contribute in this area, especially in areas of radio astronomy, because the far side of the moon is radio quiet, at least now, until we start setting up communication networks. We've got to watch that. But allows us to peer into the universe through a whole new lens, if you will, in the radio. With some very simple capabilities to do laser ranging, we can we can test Einstein's theory of relativity, essentially. We can improve our measurements of the moon's position, and that allows us to do some general relativity tests. So that one's something that we should be able to accomplish quite easily from the outpost. So that's nice. It's a high priority thing. And frankly, we feel that there's a need to just explore the moon as a potential for things like optical observatories. There's a lot of debate about how significant a problem the dust is going to be for things like Roger Angel's proposed telescopes and other large telescopes on the moon. So we need to do some site surveys, just like you do here on Earth, before you build a telescope in a location. And so those are things that we'll no doubt be doing. Next. And so here's how we assess the longer list of astronomy and astrophysics objectives. There are some things that require fairly moderate capabilities, like the laser ranging, and that could be done near the outpost. There are lots of things, though, that are bigger than that would probably require a lot more payload capability and a lot more mobility to get yourself away from the outpost. And for those, we put them as orange, which means that basically they're likely to be a little bit further out, beyond 2025. And then there's a couple of things there that require some simple sensors at non-outpost sites, so those could be done robotically, and they're pink. But again, there's a lot of good green stuff there that could be done in astronomy and astrophysics. And the community's excited about competing for small payloads that could do astrophysical observations from the moon. Next. Heliophysics, the study of the sea of energy that we all swim around in. It's generated by the sun, and how that interacts with the Earth and the moon is a big science area in the Science Mission Directorate at NASA. And this is another group of people that's very excited about the possibility of observations from and near the moon. So, you know, the moon, as it goes around the Earth, goes in and out of the Earth's magnetotail. And so it's great if you've got sort of sensors stationed at the moon, you can kind of on a monthly basis come in and out of this magnetotail and really start to understand the magnetotail environment and the plasma environment of the moon. We can use the moon as a great exposure facility to collect and analyze the solar wind and understand the composition of our star. And finally, we can use it as an observation platform to study the sun in different wavelengths for the long term. Next. Heliophysics is great because a lot of the sensors are pretty small and pretty easy to deploy. Some things they want to do from orbit, so we're actually looking at the capability of the lunar module to kick out small satellites. That's something that is being looked at in the agency. But so there's basically most of the stuff in heliophysics is stuff that we can accomplish, and they're excited about accomplishing it, so that's good news. Next. Earth observation, the last big science area in the Science Mission Directorate at NASA. There's, again, about a dozen different objectives here. I've just given you examples, but someone was asking earlier about our capability to address the global warming issue through the vision. I will be honest, there's a big debate in the earth science community about the value of doing observations from the moon, but there are at least some that think that there are some really good things that we can do, and I think that it's going to be a matter of continuing to work that over time. So things like studying Earth's atmospheric composition, understanding the relationship between the sun and the Earth, to look at the reaction of the Earth's atmosphere to solar activity. We're in a really nice position from the moon to be able to observe the whole Earth. Unlike low Earth orbiting satellites, which build up their data in strips, if we can do it well enough from the moon, it gives us a great perspective on our own planet. Surface composition to understand land use, and finally monitoring ice surfaces, which are such sensitive indicators of global change. All this could be done from the surface of the moon, potentially. Next slide. So when we assess that, though, here's what we see. Turns out that from the polar outpost location, the Earth is only in direct view about half the time from our current thinking of the outpost location. So if you say a requirement is that you have to see the Earth all the time because you're monitoring the Earth, then we have a little problem. You have to go a little ways away in order to be able to see the Earth all the time. Now, the Earth scientists have since kind of come back and said, well, maybe we don't have to see it all the time, and maybe half the time is enough, in which case you kind of enable a lot more of the Earth science objectives. So basically things here tend to be pink and red, which means if it's a modest thing, it means it would have to be deployed robotically in some other location. If it's red, it means it's a big thing, which means it probably would need people to get it up and deployed. And since you can't see the Earth from the outpost side all the time, that means you'd have to send people somewhere else. Again, we're still sort of working with the Earth science community on whether that requirement is really true, that we need to see the Earth all the time. And we're still getting ideas on different ways we can execute some Earth science from the moon. But I actually agree with the questioner before that I think we need to take this very seriously and think about, not only how we can use the components that we're building for the VSE in order to execute missions that aren't on the moon that might help us with global warming, but also what we can do from the moon to help understand the Earth. I think all of us here were influenced by the extraordinary pictures from Apollo 8 that looked back at the moon and showed its fragility. And we're going to be having people living there seeing this all the time. I think if anything, that's going to accentuate our how much we're in touch with that issue of the fragility of our own planet. And we're going to be wanting to do things from the moon that will help us with that. Next slide, please. And so finally, in addition, we looked at these environmental characterization and monitoring objectives, things like characterize the dust environment, characterize the geotechnical properties of surface materials, understand the topography of the moon, which is something that we're going to do with the Lunar Reconnaissance Orbiter starting next year, monitoring space weather to keep the astronauts and the equipment, by the way, safe, And things I mentioned, the planetary protection, evaluating astrobiology protocols to help enable exploration of Mars and beyond. So those are the kinds of objectives that we have there in those areas. Next. And these are, again, mostly things that can be accomplished quite well by placing the right relatively small sensors at the outpost location. So you got a lot of green there. The monitoring space weather one is the thing that's red up there, and the space weather community feels very strongly. You don't actually do that at the moon. You can do some of it at the moon, but you do a lot of it upstream of the moon, so that you can sort of have that early warning system. And so this is something that's not going to be done as part of the lunar exploration program, but it's something that needs to be coordinated among the Science Mission Directorate and the Exploration Systems Mission Directorate in order to make sure that we have the data we need to keep the astronauts and the system safe. And the good news is those conversations are taking place in earnest right now. Many people are talking about how the programs can work together to accomplish the vision goals. So this is really great news. And I'll tell you, it wasn't always happening a few years ago. So it's very exciting to see the whole agency really orienting themselves towards making the moon program a success. Next. So again, just to kind of summarize the things that weren't green here, the stuff that was yellow in these charts is things that require fieldwork and sampling at the outpost plus at other places. And so those are things that we really would like to see some potential sortie missions with astronauts to other sites. It's something that's under discussion. We need to have that conversation about the science importance of those objectives and understand kind of how that'll work within the capability of the program. And finally, the pink things are things that require robotic exploration at other sites beyond the outpost. And again, that's something from a science perspective we'd really like to see. So we're working on trying to figure out how we get that into the program. Next. So then just to finish up, we're in the middle of, and Neil mentioned this, LAT phase 2, which we're continuing to work, and we don't really have results that we can show yet. So just sorry to not be bringing you perhaps the most current stuff, although I've peppered in a few details there. What we're doing for the science perspective is, we've got this sort of 500 kilograms, and what we've done is we've had a meeting with the science community in Tempe in February, the Tempe Lunar Science Workshop. Some of you may know that we had workshops before Apollo and Woods Hole that were sort of famous as to where they kind of laid out the science program, and lots of the plans flowed from that. But we brought a very similar presentation to that Tempe workshop, and had about 250 scientists there help us with priorities in science, help us thinking about different ideas for how we accomplish those science. And we've taken those inputs now, and we're starting to do some reference designs for various packages, an environmental monitoring package or a geophysical monitoring package, and looking at geological tools and what might need to be on a rover in order to collect the right information, as well as a lab in the HAB. We're going to get lots and lots of rocks, and you want to be able to do some high grading there on the moon, since you're going to have some time to figure out what are going to be the most critical samples to bring home, and which things you can leave and make your nice rock garden there outside the outpost. And in addition, we're looking at sortie sites of high priority and what kinds of tasks we might want to accomplish at those sites. So places other than the outpost that for science we might want to go. So it's a very exciting time in that we've got the science community engaged in what we're doing, and we've got the scientists across the agency, and literally this is a multi-center effort to bring in the best and brightest, because as you can see, we've got a huge diversity of disciplines that we're trying to represent for this effort. So it's an exciting time moving forward. I think that science and exploration at NASA are going to be working closer and closer together as the years go on here. And hopefully in, 12, 13 years, I'll be up here reporting our first scientific results from the human exploration of the moon. So thank you all, and I'm happy to answer a couple of questions now, or maybe one or two, but also encourage you to come at 2 o'clock and we can have a broader discussion here of science and the lunar architecture and things like that. I'm happy to answer questions there that didn't get answered this morning in Neil's presentation as well. Thanks. I see a question out there. Go ahead, sir.
Hi, I'm Hugh Davis. I was a part of the Apollo 11 mission.
Right on.
And my particular interest is what do we know now and what do we hope to learn about the origin and composition of massive comets?
We don't know very much about the concentration, about the composition beyond what we've learned previously. We had We've had a couple of missions go to the moon since Apollo that have done some compositional maps, but we've got a very exciting one coming up on the Chandrayaan spacecraft. We've got the Moon Mineralogy Mapper that's going to go and just blow our socks off with compositional information. And so then we'll finally have the data that we need to be able to correlate with some of those sites. So stay tuned. It launches next year. I was just talking to Paul, we think next April. And that's going to provide us incredible information about compositional diversity on the lunar surface beyond what we've had before.
I hope we'll look for Sudbury.
Right on? Yes.
I'm Fred Ordway. I was quite intrigued by the using the moon for Earth's surface and atmospheric and ice. I hadn't seen much of that, at least in the literature.
Right.
And the question in the previous session that we just came from had to do with global warming. Now, if that's something that is very valuable, that we can do things from the moon that we can't do from orbit, or we can't do from geologists on the
Right.
Greenland ice cap, for example, or the big teams in Antarctica, how valid is that?
Right, and that's the question exactly. You hit the nail right on the head. Are there unique things that we can do on the moon that we can't do on the Earth, or that we can't do from low Earth orbit? And so I will tell you that I don't think we have the answer to that yet. I think that some of the Sun-Earth interaction observations, sort of that you would like a little bit more standoff distance from, those kind of things, I think it'll be pretty easy to make the case that we can do some great things since we're going to have that great capability on the moon. But things like observing the ice sheets and understanding atmospheric composition, it's not at all clear that the moon provides a significant advantage. So those are the kind of questions that we have to ask. On the other hand, we are going to the moon. We're going there with people. We're going there with the capability to service things. I think that there's a case to be made that, that it might well be a wash, and if so, why not use the moon as the platform that we're developing it for? So stay tuned, because those are going to be the subject of really active discussions over the next year. We just had the first set of discussions with the science community, 2 months ago about this, so it's a very exciting time. Thank you all again. Thank you.
Thank you, Laurie. That was fantastic.